we have considered the governing equations for steady state of flow, that is the general groundwater flow equations we have derived, and then the steady state simplifications or the steady state radial flow to a well has been discussed, considering both a confined aquifer as well as an unconfined aquifer. So these equations have been derived, and based on this, we have considered several problems on steady flow to wells in both confined aquifers and unconfined aquifers. Now, the next topic we have to consider is the unsteady radial flow to a well, that is the transient flow. Now, if you consider the unsteady flow, the term which you are seeing in the last line of this slide, that is dou square h by dou r square plus 1 by r dou h by dou r is equal to s by t dou h by dou t. So that is the equation. In fact, now I remember that I have covered this also, and we have stopped at the stage where the well function is being defined. So here there was a small confusion, and so here we have stopped. But anyhow, I will proceed from the beginning. So if we consider the confined aquifer case, when a well penetrating into an extensive confined non-leaky aquifer is pumped at a constant rate, so here the aquifer is confined and it is extensive. Extensive meaning that its extent in the both lateral and longitudinal directions, transverse directions, are infinitely large. And it is a non-leaky aquifer, and the well is penetrating throughout the width of the thickness of the aquifer. Somebody has joined. I will allow them and then proceed. Okay. So, for this case, the rate of decline of head when multiplied by the storage coefficient, that is rate of decline of head means dou h by dou t. You are seeing here dou h by dou t. So this dou h by dou t, when it is multiplied by the storage coefficient capital S, and when it is over the entire area, this must be equal to the discharge. So the applicable equation will now become this one, dou square h by dou r square plus 1 by r dou h by dou r. So this is equal to the product of S by T and the rate of decline of the head with respect to time. So this is the time rate of change of discharge, and this is the spatial rate of change of head over the entire extent. So these two, when these two are summed, that must be equal to the rate of change within the given time, during the given time. So this is dou h by dou t. So here h is the head, r is the radial distance from the pumping well. So we are considering any well which is located at a radial distance of r, or any point. It need not be a well, it may be a point also. So at that point there will be some water head. So that head is indicated by small h, and the distance, radial distance from the center of the pumping well, axis of the pumping well to the point under consideration is suppose if you consider this as the pumping well, suppose this is the pumping well, and I am considering any point from the center of the well. So this distance is R. Small r. So at this point, we are referring this value of H and S and T are defined for the aquifer as a whole. Aquifer as a whole. So this equation is to be solved. Now, Thies obtained a solution for this equation based on the analogy between groundwater flow and heat conduction. So, by assuming that the well is replaced by a mathematical sink of constant strength and imposing the boundary condition H is equal to H naught, that is the initial head corresponding to initial time t is equal to 0. And again H is equal to H naught for any time at an infinitely large distance r being infinity measured from the axis of the pumping well. So with these boundary conditions, the solution is given as follows. So this is the equation solution. Small s, this is small s, is equal to q by 4 pi t integral of a dummy function, dummy derivative u, changing from u is equal to u to infinity, e to the power of minus u by u du. And this is given by the entire expression within the integral symbol is referred as well function. So this is called as well function. So therefore, our equation is S is equal to, the small s is equal to, that is the drawdown is equal to, which is at any time t, which of course is at any time t. So the drawdown at any time t is given by q by 4 pi t, this is capital T, which refers to the transmissivity coefficient multiplied by a function which is called as well function. Now, the well function u is defined as r squared capital S by 4 t t. So this well function value will be varying from any time t is equal to 0 to any other time t. So in this expression, you can substitute the value of t starting from 0 to any other time. But of course, t is equal to 0 is not defined because u will be infinity. So t greater than 0. T is greater than 0. So if you consider any time, say for example, 1 hour. So you are interested to find out the drawdown small s corresponding to a time of t equal to 1 hour at a point which is radially located at a distance of r, say for example 5 meters. So we can now find the drawdown at a point which is at r is equal to say 5 meters, corresponding to a time t equal to 1 hour, the point being located at the distance 5 meters from the axis of the pumping well. So that at that stage and time, at that location and time, the drawdown small s is given by Q divided by 4 pi t into well function. So if you keep the well function for the time being away, so in this expression, Q is the known value of discharge and T is supposed to be the known value of the transmissivity coefficient, and WU is the well function, which we can calculate following two methods. One is a table for well function. A table for this well function is given for different values of U, or you can use this expression given in the brackets in equation 1. So this total equation 1 is referred as Thies equation and is widely applied in practice and is preferred over the equilibrium equation. The reason is equilibrium equation considers that throughout the time of pumping, throughout the period, the discharge is being pumped out at constant rate and same head is maintained. But in fact, though the discharge is maintained constant, the head will be changing at any location from time to time. So that means the cone of depression, which is formed due to pumping, will change from a horizontal line at initial time t is equal to 0 to some different values at different times. So therefore, it is not a constant cone of depression. So it changes with time t. So we therefore use this equation, and the value of storage coefficient S can be determined using this equation and the data of the pumping test. So for example, if we have a pumping well and start pumping from the well at a constant rate S, if we know the value of T, we can use the measured value of drawdown and find out the storage coefficient S. We can also find the transmissivity also. So only one observation well is sufficient in this case, whereas in the case of equilibrium equation, that is the steady state case, we require at least two observation wells for determining the values of S and T. So that is the difference between the equilibrium equation and the Thies equation. Then a shorter period of pumping is generally necessary, because if you want to apply the steady state equation, you have to continue the pumping continuously for a long time until you arrive at such a stage where the cone of depression is maintained unaltered from time to time. So it takes a lot of time, and therefore the effort that is involved is much more compared to the test that will be done using the unsteady flow. In case of steady flow, a lot of time is required. No assumption of steady state flow condition is required, obviously. However, the assumptions inherent in equation 1 should be emphasized because they are often overlooked in applying the non-equilibrium equation and thereby can lead to erroneous results. So, even though the equilibrium, the his equation is superior over the equilibrium equation, there are certain assumptions involved in this case also. And what are they? These are the assumptions. So the first one is the aquifer is homogeneous, isotropic, of uniform thickness and of infinite areal extent. That means the properties of soil are the soil properties of the aquifer. That is, when you consider the coefficient of permeability or coefficient of transmissivity is to be same in all directions. Kx is equal to ky is equal to kz, each is equal to k. And that k when multiplied by the thickness of the aquifer b, it gives you the transmissivity T. T is equal to is the product of K and B. T is equal to KB. So, unless otherwise we consider the aquifer to be isotropic, we cannot eliminate the parameters associated with Kx, Ky, Kz and equate all of them to K. So, that is one assumption. Homogeneous. Homogeneous means, in fact, first the requirement is homogeneous, then isotropic. Homogeneous means the aquifer should not contain different types of soil structures within itself at different locations. That means you cannot have a pocket of, say, for example, sandy soil and a packet of silty soil or coarse sand in different pockets over the entire aerial extent. So now what we consider is that the total aquifer is extended, which is considered to be extended over infinite distance. That infinity means long distance, is to have the same type of properties, same type of soil classification, same type of soil parameters or distributions, soil size distributions, and soil structure arrangement. That means the arrangement of the particles. So that is homogeneity. Then isotropy means same properties. The values of Kx, Ky, Kz, etc. are same. And then uniform thickness. It cannot be undulating thickness, varying thickness. The thickness of the aquifer, which we are considering as B, is uniform throughout, and it continues to be for infinite aerial extent in all directions. Not all directions, in both x and y directions. Z direction, of course, is limited for us. Now, before pumping, the piezometric surface is horizontal. So, that is, of course, is not a real assumption, because in most of the cases, the piezometric surface will be horizontal unless otherwise there are certain varying surcharges over the soil. So, the well pump is pumped at a constant rate. That means Q is maintained as constant. The pumped well penetrates the entire aquifer and the flow is everywhere horizontal within the aquifer to the well. That is the fully penetrating well assumption. And the flow is horizontal. When you consider a well, like this, and like this, So at any vertical distance, always the flow is horizontal. This is horizontal. That means although your cone of depression is something like this, so this is your cone of depression. So naturally, the flow will be more or less parallel to this, like this. Especially near the close to the piezometric head. So we assume that in this case also the flow will be like this, horizontal. So this is our most important assumption which is required to be considered. Otherwise, the flow cannot be, I mean, the solution cannot be obtained. So that is the meaning of this part of the assumption. Everywhere the flow, everywhere horizontal, the flow is horizontal everywhere. Okay. Then the well diameter is infinitesimally small. That means the diameter of the well is small, so that storage within the well can be neglected. If the well diameter is large, then what happens is there will be storage in the well, some additional, because some inflow will be coming and some outflow will be there. So there will be a relative storage sometimes. So therefore, to avoid that situation, we consider the well, the pumping well diameter is small. Then water is removed from storage is discharged instantaneously. Obviously, when the storage is small, then whatever amount of water is entering into the well is being removed through your pumping. So water is removed from storage, whatever is removed from the storage within the aquifer, and that enters into the well is instantaneously discharged out. So if there is a declination in the head, immediately that is proportional, that will be the discharge is made proportional to the change in the declination. So this is what these assumptions say. Okay. Now, so with these assumptions, we will proceed to the solution to the non-equilibrium equation. So there are, I think I have covered this also. All of you respond?
Briefly
Huh? This is what this is where we have done. I now remember we have done the problems also. Chesankara, we have done this problem.
Yes, sir.
ఎస్ సార్ ఆల్రెడీ చేశాను సార్, కాకపోతే మళ్ళీ ఇంకోసారి ఎక్స్ప్లెయిన్ చేస్తా
Okay.
అన్నారు సార్.
Okay. So now is it clear to you about the well function and this method? I think I covered all the methods. All the three methods I have covered, isn't it?
Yes, sir.
This well function table also I have explained. See, how to calculate this well function is available. 1 minute. See, this is the expression for well function. U. So R squared S by 4 TT. So now I will explain this problem once again so that your memory will be again recalled. Today I will recall your memory. So here in this particular example, we have the values of Q, T and S. Q is the discharge, T is the transmissivity and S is the storage coefficient. Now here you are required to calculate the drawdown at a point of 1 kilometer from a well after 1 year. So this is the example. 1 minute. Okay. Okay, right. So I will explain from this point onwards. So suppose we know the values of S and T, then we can use this equation for determining the drawdown at any point, which is now, in this case it is 1 kilometer, and at any time, which is 1 year from the starting of the pumping. So here the assumption involved is the pumping is continued for a period of that 1 year. Otherwise, there is no meaning. So this is the value of U. Because what is the expression for U? U is given by this. Small u is equal to R squared S by 4 T T. So in this case, R is 1 kilometer, that is 1000 meters. So R squared is 1000 square, and capital S is given as 4 into 10 to the power of minus 4, and capital T is given as 600 meters square per day. So this is 4 into 600 meters square per day, and small t is 1 year, that is it is 365. So once when you substitute this information, you will get U as equal to 4.6 into 10 to the power of minus 4. So you enter into this well table function, well function table, and match the value of U with your calculated value of U in the table and read the value of well function. All these values here all these values shown here. One minute. Okay, all these values shown with this yellow background refer to the values of well function u, w, wu for different values of u. So, starting from u is equal to 1, 1, u is equal to 2, 3, 4, 5, 6, 7, 8, 9, and 0.1, this refers to 0.1, 0.2, small u is equal to 0.2, small u is equal to 0.3. So, now what is the value of u for this highlighted value? All of you note the values of u, value of u corresponding to the value of wu, which I have shown as 22.67. What is the value of u? All of you?
8 into 10 power minus 11, sir.
Yes, 8 into 10 to the power of minus 11. So, 8 into 10 to the power of 11. So, suppose if I consider this, it is 4 into 10 to the power of minus 7. Okay? So, the value which I have now I highlighted is for u is equal to 4 into 10 to the power of minus 7. The value of wu is 14.15 into 10 to the power of, that's all, 14.15. Okay? Do you understand this point? All of you?
Yes, sir.
So this is how we can get the value of u, get the value of wu for a calculated value of u. Now, in the present example, this is 4.6 into 10 to the power of minus 4. So, but here we have the values of well function for 4 into 10 to the power of minus 4 and 5 into 10 to the power of minus 4. So, what we have to do? We have to interpolate between these two values. So, that interpolation has resulted this value of wu for this value of u. Okay. So this is how we make use of the this equation for calculating the drawdown at any point corresponding to any time. But now we will consider the other usage of this equation. This equation and this method, which I am going to explain, is given by Thies. So the Thies method enables us to calculate the Ackford constants, that is capital S and capital T, by conducting a pumping test and observing the drawdown in one single well, which is located at some distance R from the pumping well. The only requirement in this case is that we should note down the values of the drawdown starting from the beginning of the pumping, which is considered as T is equal to 0, continuously over a long period of time. So that data is to be made ready for application of this method towards the calculation of the Ackford constants. So the first step in this method is to get a type curve. The values of observed drawdown S from a pumping test are plotted against the values of R square by T on a logarithmic paper, which is of same size and scale as of the type curve made available in step 1. So we assume that a type curve is available for a particular size in a particular size and scale. Now we use the same size and same scale for plotting the data of small s measured at any distance R for various times small t. So the observed time drawdown plot is superimposed on the type curve. So the next step is the superimposition of these two. But while we are doing this, we have to keep the axis of both curves parallel to each other. So we cannot.
Excuse me, sir.
Yes. So the observed the two curves are kept parallel to each other. Then once we arrive at this stage, then we will select any one point, any one convenient point, and we note these 4 values, that is values of WU, small s, R squared by T, corresponding to that point, because that point will show values of U and WU on the type curve and values of S and R square by T on our plotted curve. The values of observed drawdown from the pumping test are plotted against the values of R square. So the graph referred in point number 2 gives you the values of S and R square by T, and the type curve referred in point number 1 gives us the values of U and WU. So from these recorded values of WU, U, S, R square by T, the values of S and T can be calculated using equations 1a and 2a. I think I have given 1a and 2a above. This is 1A and this is 2A. Because in this expression, we know the value of small u and well-functioned WU from the type curve, and we know the value of S and R square by T from the observation plot. So, the parameters small s and R square by T, which are on the left-hand side of equations 1A and 2A, will be read from our plot referred in point 2 mentioned earlier. And the values of U and WU are obtained from the type curve mentioned in point 1. All these four values refer to a single point, which is a convenient single point selected on the both of the sheets when put together. So we need not consider any point to be lying on either the type curve or on the observation plot. It can be any point. So there is no restriction for selection of the point. It can be on the plot or it can be below the plot, but within, of course, the graph sheet. So this is now the method. So this is your type curve. Now here I am. Okay, it's not possible. So this top one, I will highlight it. This is the type curve. So the brown one is the type curve and the yellow one is our, the yellow one is our type curve and the brown one is our observation plot. So the circles which you are which you are seeing here are our data points, and the full line is your type curve. So you can see that I have selected a match point which I have highlighted with the blue color circle. So the values of U, WU, S r square by t. See, here you are having S here. This is S. So you will get this as r square by S. So this value, which is I think slightly lower than 0.2, which is indicated as 0.18. This is 0.18. That is yes. And r square by t is I think 150. Okay. Then so this is your small u. So this is how we select the match point and the corresponding values of S, r square by t, u and wu. So these four values are used and the solution is obtained. So that is your Thies method. Right. Next, the second method is a simpler one, and it is Cooper and Jacob method. And in this method, the expression for well function, which I have given earlier, see, this is our original expression. This is the expression within the square brackets is well function. So which I have which I am showing in the yellow background. In the green background is your well function. So that well function expression is now assumed to be truncated beyond the second term. That is the first term constant minus 0.5772 minus log u, where u is your r squared s by 4tt. So all the other terms starting from u to I will remove this because this is only so all the terms beyond this are removed, neglected. So therefore, your simplified equation will be now this one. So this equation is rearranged by replacing natural log to the log base 10, and then so when you plot this s versus log of u, that is r squared 2.25 that minus 0.5772 is also replaced by converting it into something to the log of something to the base 10, and everything is now combined, and the total expression will now, the expression equation 3 will now take the shape shown in equation 3a. So it is s versus logarithmic of tt by r squared s. So if you consider that that everything in the logarithm sign is some y, some x, and s on the left hand side is x, is y. So y is equal to k log x, where that k is 2.3003 q by 4 pi t. So if you plot a graph between y and x on a semi-logarithm sheet, it will be a straight line. So equation 3a follows that s versus log of this thing, it is a straight line. So plotting this line and projecting this to s is equal to 0, where t will be t0, we will now have, that is the expression which we get. So therefore, using this, we will get this equation. Log 1 is equal to 0. So on the left hand side, if you just replace it by log 1, so we will get this expression. So therefore, a value for t can be obtained by noting that if t by t0 is equal to 10, then log t by t0 will be 1, and therefore replacing s by delta s, where delta s is the drawdown difference, where delta s is the drawdown difference per one log cycle of t. So, this will now be the simplified equation. So, this is our final equation for t. So, when once t is known, you can calculate all the other things. Now, the only restriction or limitation for application of Cooper and Jacob method is that the straight line approximation for this method should be restricted to small values of u which are less than 0.01 to avoid large errors. So, go back to the original expression for u. What is the original expression for u? This is the original expression for u. So, your value of u must be less than 0.01. So, you choose your r and t, small t and r in such a way that this value of u will become very small. So, because there is no initial information about what could be the value of r, s and t, it is always better to consider the value of small t such that it will be very large value, so that u will become very small. So, that means you have to take or you have to conduct the test for a longer period to be able to apply the Cooper and Jacob method. So, that is the limitation of this method. Now, have you followed this Cooper and Jacob method? Now, we'll consider the third method, Chow's method. With this, I will stop and we will continue other part. So, Chow developed a method of solution with the advantage of avoiding curve fitting and being unrestricted in its application. In this method also the drawdown measurements in an observation well are made. See, the drawdown observations in an observation well are necessary, bare necessary for proceeding with the determination of the aquifer constants S, capital S and capital T. So, the solution procedure is as follows. The observational data are plotted on a semi-logarithmic paper in the same manner of Cooper and Jacob method. On the plotted curve, an arbitrary point is chosen and the coordinates t and s are to be noted. Next, what we do is we draw a tangent to the curve at the chosen point and we will measure the difference in the drawdown for one cycle, time cycle, one cycle log cycle of time. So, that is what we do. Going back to the graph, I will show you. Suppose let us assume that this is our curve. You forget everything. You forget about those colors and other things. Only just for explanation purpose, I am using this. Now, what I do is So I have drawn a tangent. Now what I will do is, I will consider so. Now what I have done is, this is my, the curve which is shown here is S versus T. Forget about this R square by T. It is not R square by T, but it is only T. So this is T, X axis is T, and Y axis is draw down small s. And these are our plots. So now I considered some convenient point here. Yeah, I had taken a convenient point here, and there I had drawn the tangent. Now, after drawing the tangent, then I have selected one time cycle. So this is one time cycle. So now I have noted the difference in the drawdowns. This is delta S. So this is delta S, and this is T by T naught will be 1. So So this is what we had done. A tangent to the curve is drawn at the chosen point is to be drawn, and the drawdown difference delta S in appropriate units per one log cycle of time are noted. So the next step is using the values of drawdown S and delta S noted, a function fu which is equal to S by delta S is calculated, which is related to the well function WU, as WU is equal to 2.3 times FU. However, this relation is valid only for the values of FU greater than 2. So from this value of FU and WU is arrived because we know FU, we know S delta S, and therefrom the value of U is calculated using the tabulated values of U versus WU. So subsequently using the relation S is equal to Q by 4 pi T WU and R square by T is equal to 4T S by U, this storage coefficient S and transmit state T are obtained. So this method, I think, see, this is the one. Now this is our drawdown, yes, and this is our time. So you can see this is logarithmic scale and this is ordinary scale. So these are your pumping values, these pumping test data. It so happened that they are almost on a straight line. They may be anything. For example, you may have I'm just looking at the thickness of this. Say, for example, this is your curve. Need not be these points which I have shown with circles. Suppose this is your curve. Then choose one point and draw a tangent there. And now note the values of S and T. Now do you understand?
Yes, sir.
So now that is the calculations. Now the value of S and T are known. Let me note what are those values. Small s is 0.47 and small t is 6. So you can see in the calculations, see small s is taken as 0.47 and t is calculated, capital T is calculated. Prior to that, FU is calculated. So your delta S is 0.38 and your S is 0.47. See, your S is 0.47. Okay. And so therefore, FU is S by delta S. Small s is 0.47, delta S is 0.38. So S by delta S. And multiply that by 2 point, what is that value? .3. WU is 2.3 FU. So 2.3 into this will give you 2.75. So this is WU. Now substitute WU, Q, S. You get T. And use this value of T in this equation. For capital T, small t. Now what is the small t? Small t is from our point of tangency. So it is 6. So this is how we get the value of capital S. Okay, have you followed Chau's method? So I will stop here today and we will continue tomorrow. Tomorrow at what time? Our original class?